University of Catalonia, Polytechnic of Catalonia, on a quantum dipole in 2 dimensions. So,
Thank you, Lauren. I speak a bit loud, so sorry if it's too loud. So thank you to organizers for inviting me and giving me the opportunity to explain what we are doing in the last years in my group, what is called this Barcelona Quantum Monte Carlo group in the Technical University of Catalonia in Barcelona. Okay, this is a work made along the years with my colleagues, Ferran Mazzanti and Grigory Stakarczyk, and also former students, Raúl Bombín, Juan Sánchez, Grecia Guijarro from Mexico, and also my colleague, Mari Carmen Gordillo, for a long time. So let me try to see if it works. It worked. Okay. So the outline of my talk will be the following. So I will so my approach, which is a microscopic approach to the problem. Okay, so our method is based on these quantum Monte Carlo methods, which are ab initio in the sense that we start directly from the Hamiltonian of the system and we solve the many-body problem in principle in an exact way. I will comment about that. I will comment about superstripes. There's a fashion way of producing a kind of supersolid using tilted dipoles in 2 dimensions. It connects with the talk before by Lorien. I think it's a lot of interesting physics to do in 2D. I will show our results about this Baker-Tay phase transition that has been discussed here for a long. I will show how is our perspective as people doing microscopic simulations about this Baker-Tay transition, how we get this. Then I will discuss a funny system, which is bilayer system. So imagine that I have 2 layers of dipoles, and there is a lot of funny things that emerge with this dipolar setup. I will try to show you. In particular, I will show that you can have an ultra-dilute liquid with dipoles playing with this bilayer geometry. I think it's a very interesting result. Hopefully someone experimentalist can check if this is work or not. This is a theoretical prediction up to now. And as I will comment also, I will show you that even you can get solid phases, which is even more strange, using dipoles in a multi-layer geometry. If I have time, I also will comment about all the stuff in the sense that is helium, but helium on graphite is a very rich system. And I will show you that even in that case, which is a 2-dimensional system, we see some supersolidity in the system. So first, some words about the methods. Diffusion Monte Carlo was introduced by Silvio, so I will not carry a lot of time with this. So the idea is that we start with the Schrödinger equation. H is the Hamiltonian, E is a constant for the problem. And then look at here, this is written in imaginary time because we are searching for the ground state. And then what we make is essentially we expand the wave function, which depends on the time, in the full basis of the Hamiltonian, okay, in a standard fashion. But now there is not the I here, so this is the decaying exponential term. So this is our eigenfunction. So the principal idea of all the projection methods is that when this imaginary time goes to infinity, so in this combination of terms, only the ground state survives because it's the one with the lowest energy. So this is a projection method. So then running out this at the style of Green's function, the idea is that you get the ground state of the system, of a many-body system. So you are really solving the many-body Schrödinger equation that you know is very hard to solve. So for bosons is exact within a statistical noise. For fermions, we have the same problem that Silvio also commented. That makes that the solution of this is just an upper bound. A good upper bound, but an upper bound. Yes. Diffusion. Why is called diffusion? Because when you split, okay, here are more work to do. You write this in terms of the Green's function of the system. So you write this, the Schrödinger equation in integral form. And the Green's function at short time, the part that comes from the kinetic propagator is just a diffusion in imaginary time. So it's like a classical diffusion. This is why it's called diffusion Monte Carlo. So diffusion Monte Carlo is a diffusion process. And then there is a drift force that is a technical question, moves the walkers. Walkers are the configuration points to the regions where are interesting, are large. And then there is what is called the branching terma. It's a bit technical, but the name diffusion comes from the kinetic part. So a second approach to get the ground state is what is called this path integral ground state method. This is an alternative to the first one. The name is really ugly, so big pics is not a good. It's okay, but I am habituated, yeah. But the first time that you see this is why you use this, because this is path integral ground state. Some people call it variational path integral, okay, but it's the same method. Well, the idea is again a projective method. So the idea is that you use the propagator in imaginary time, but then a difference with the previous approach. What you make is just you put a boundary condition and you propagate this wave function using the Green's propagator here, but just for a short time, okay? So then the final wave function comes from this kind of movement here, okay? This kind of bit or polymer, if you want, that you move along the space. So every one of these polymers represents a particle. Okay, and this polymer moves along the time and interacts with other polymers which represent other particles. I will comment now the version at finite temperature, which is even better to show this behavior. This is Feynman ideas, in fact, okay, but translated to the codes. So the idea is that this method is sometimes more flexible than diffusion Monte Carlo, and the influence of the trial function that you need to put here in the extremes is just very small. So just you need to ensure that the wave function, for instance, if you are computing bosons, this trial wave function has to be symmetric under the interchange, and that's all. And the method works perfectly well. And also technically, because this method allows for a good calculation of the one-body density matrix, which is a real important quantity to know the coherence of a system. In the case of diffusion Monte Carlo, technically, it's not perfect, so we have a bit of bias, but in that case, it's exact, okay? But then if you go to finite temperature, because we want to study this Baker-Tate transition, we need an algorithm that is able to move the system, to calculate the properties of the system at finite temperature. And this is what is called the finite temperature path integral Monte Carlo. Again, now is not written in terms of the wave function, you know, because you are now at finite temperature. So the language now is the thermal density matrix, which is, as you know, the exponential of the Hamiltonian, where beta is the inverse of the temperature. Okay. Then if you are able to access to this basis, every expectation value, you know from a statistical mechanics that can be solved in this way. Okay, where Z is the partition function. If you project in the coordinate space this equation, okay, you can get this expression here, in which it appears this term, which is the spatial representation of the density matrix, so written in the basis of the Hamiltonian. So the idea is that you need to calculate this density matrix or to have an estimation of the density matrix, and then to sample any operator through this relation. The good thing about the density matrix is that, as probably you remember from quantum mechanics, it can always be decomposed in the following way. So it follows a convolution property. So in such a way that at a given temperature, beta is the inverse of the temperature, you can make the convolution product of two density matrices, but at higher temperature, at 2 times, in that case, temperature, okay? So if you are able to approximate, which is the thermal density matrix at high temperature, and you iterate this not 2, but many times, you can arrive to the temperature that you want. This is the essential idea. So we need to apply this convolution property, and to get a good approximation for the density matrix at high T. And then just iterate. As you know here, is written in this equation. Okay, this is for m terms, here is for 2, but the idea is the same. So then this problem, once you write the thermal density matrix using this language, what you see is that the problem, it is known from all times, maps to a problem of interacting polymers, if you want, where each polymer, every polymer is closed because the partition function imposes that is a circular, so you have to close by periodicity to the initial point. So each one of these kind of polymers is a particle. Okay, it's a representation of a particle. So here I have a particle, here I have a second particle. What couples these terms, which are called bits in the technical language, bits, okay, are coupled by an harmonic coupling here that comes from the kinetic propagator. And every representation of the particle, every bit interacts with the same bit of the same number through the potential. Okay, so then we have the coupling between the effect of the kinetic action and the interaction part between bits of the same size. Okay, so this is the essential idea. So in principle, you map the problem to a classical problem where particles are polymers that interact in this form. Well, here is explained. So this is the interaction between bits, and then you have interaction between different. Of course, this is technically quite involved. Okay, so here it seems easy, but then in the practice it's quite involved. Because first, using the first approximation, which is called the primitive action, it's impossible to go to superfluids because the number of terms that you need here, the number of bits is incredibly large. So the system becomes blocked. So it is a problem of slowing down. So the system is not evolving. As if you know about Monte Carlo, this is the problem that sometimes it becomes blocked because you cannot sample all the configuration space. So to improve that, you need to work a bit more on this, the coupling of the Green's function in terms of the kinetic and potential part. The first term is if you remember this Baker-Campbell-Hausdorff formula. Okay, so the first term is to decouple kinetic and potential, but then it appears the next terms, which contains commutators, tricommutators, and so on and so forth. Okay, so you can include more terms, and in such a way that these strings are a bit more complicated, not just this one, but then the number of bits that you need are smaller. Okay, so in this sense, you can go to superfluids. This is one thing. The second thing, and more involved, is that in the case of bosons, I need to ensure that the partition function has to be symmetric under the interchange. Okay, so I have to sum over all the permutations here in order to be symmetric. Okay, so we need to sample not only the space configuration, but the permutation configuration. And this is rather involved, but in the last days, in the last times, we use a proposal which is called worm algorithm. It becomes very famous in our field, in which the sampling of the permutation is becoming much more efficient. But at the beginning was difficult to sample that. Now it is sampled in an efficient way. So I think that with that, we can go to the results that we have obtained in the last years. The first thing is, let me write here the Hamiltonian. So we start with the Hamiltonian. So our approximation is ab initio. They are not being filled here. So we start with the full Hamiltonian, and then we solve the many-body problem in an exact way within a statistical noise. We have to pay a price that we have statistical noise, but there is not any bias apart from that if we work properly. Okay, so then this is the Hamiltonian. The interaction we have seen this morning, the interaction is this strange thing here, which is depends on R to the -3 and is anisotropic, as you see from these scalar products. In the case of a tidal dipole, so I will now present results on a two-dimensional system, purely two-dimensional system. But now the dipoles has a given angle with respect to the perpendicular direction. If alpha is 0, okay, if all the dipoles are perpendicular to the plane, the interaction is just this 1 over r to the 3. So is isotropic. Okay, then the problem is easier. We solved that many years ago. It crystallizes at high density and so on. But if you just turn the dipoles just tilt an angle with a magnetic field, then it appears the anisotropy immediately, okay? In the sense that two dipoles in this direction are repulsive, but in this direction are attractive. So we have the competition in two directions in the plane. These are repulsive and these are attractive, okay? So that produces a rich phase diagram due to the anisotropy of the system, and also due to this quasi-long range behavior of the potential. And this is what emerges from, for instance, from our calculations. Here, from top to bottom, we have n is the density, so we have several densities, and we can also change the alpha, okay? By the way, as there is not any two-body potential, I have to, there is a maximum angle alpha in which the system is stable. So if I tilt more and more the dipoles, the system collapses because the system becomes attractive. So this term dominates the repulsive one, and the system is collapsed, okay? In order to avoid the collapse, we need to put a two-body correlation, but in this case, it's not introduced here. Okay, so we see here what happens. For instance, this is the static structure factor. The static structure factor, which is the Fourier transform of the pair distribution function, is a quantity which is very important to characterize order in the system, okay? Because if the static structure factor shows, say, a Bragg peak, it means that you have a crystal, for instance, okay? So if you look at here, this is the simulation in this S of k in the x and y direction, okay? You already see, even when the density is low, forget about this black, we see that the two S of k's are different, and one has a small peak here, okay? And the other one is more smooth. This is how it appears, the simulation in our language. This is what is called a snapshot. So we plot all the bits for all the particles, and we have a representation of our system in the simulation, okay? If you increase the density from 64 to 128, keeping the same angle, we see how this red peak starts to grow, whereas the second, the blue, is more or less the same. What's the red and what's the blue? The red corresponds to the direction in which the system is repulsive, okay? And the blue is the one in which are attractive. Okay. So if you look at here, well, it seems that something starts to happen, but it's not clear at this scale, okay? But if you increase a bit more the density, or even increase the angle, and you go close to the critical value before collapsing, you see here the formation of a Bragg, really a Bragg peak. Look at here the scale. The Bragg peak means that the height of the peak is of the order of the number of particles. This is the idea of a crystal. When I have a Bragg peak, the peak is more or less proportional to the number of particles. So you see that here, there are two peaks. Instead, this blue have some structure, but still not very important. But if you look at the configuration, the snapshots of the system, you see how the system, I have no perspective here, but probably you see that it starts to appear in ordered system, okay? The system, it starts to appear organized in bands. And that's the reason why, looking at S of k in the transverse direction, you see order, okay? The order is clearly shown by the S of k, okay? So the main characteristic of a crystal, from a microscopic point of view, is to calculate this S of k. So that can also even observe it in the what is called the two-body radial distribution function that shows the probability of finding two particles at a given distance. And you see that when the system is say, far from this formation of stripes, you see something here, but not relevant. But when you arrive to this regime, you see the formation of these bands, okay? What is produced here is a stripe phase. This is called the stripe phase. So the system organized in bands separated by the vacuum or quasi-vacuum. And then the diagram is quite rich. We determined several years ago how is the phase diagram of the system as a function of the density and the angle of this tilt phase. Okay, we have three phases. Here is the collapse that I commented. So if I cross the critical value for the tilt, the system collapses to a point, so it's no more a phase. We need to put something more in the Hamiltonian. But what's nice is that we identify three phases: a gas, normal gas, with some anisotropy, but still a gas. We have a crystal, a triangular crystal that we can see. And more interestingly, we see this phase here, which is called the stripe phase, which is, I think, is very interesting to explore, because I will comment that this stripe phase, in fact, in some parts is a super stripe in the sense that it's super fluid. We checked that from the gas to the stripe, this phase transition is second order, according to our results, looking at the scaling of the functions. From gas to crystal is the first order. From stripe to solid, we don't know, because honestly, was extremely difficult to calculate this line, so we are not sure about this. But it's interesting that if you look at here, starting, for instance, at 340 or near 400, the system starts to be solid. But if I increase the tilt, I cross to a gas. That's curious. No? So from solid, I go to a gas. The system is not so repulsive, but then goes to a stripe. So there's a double phase transition at a fixed density, which is not so frequent. We are at zero temperature, okay? No, it's not a final temperature. This is just due to the anisotropy of the interaction. The problem with that, for experimentalists, is that the density of the stripe phase is very high. This is in what is called dipolar units. It's too high, I think, to be accessible from experiments, okay? But we also worked in another system, which is called the spin-orbit coupled gases. In the spin-orbit coupled gases, the stripe phases also appear. And we showed that this is also a super stripe. And there, the density is much lower. So I have seen several drawings from an experimental group, confidentially, that they show that they have observed these stripes in these spin-orbit systems. Probably will appear in Nature or Science very soon. Well, but this is not enough, because we can try to understand if the system is or not superfluid, okay? And we have the tools for doing that, because we can calculate in our system what is called the one-body density matrix. Okay, this, you know, we have seen that before, okay? The idea is that if we see a flat behavior along distance of this quantity, you will have a condensate fraction, okay? So a condensate. Remember that we are at zero temperature. It's 2D, but zero temperature. 2D at zero temperature has a condensate, not quasi-condensate. Is when you put temperature that becomes a quasi-condensate. So, okay, so in 2D at zero temperature, we still have coherence. But also we can calculate the superfluidity, and that's nice. So we can calculate the superfluidity. Technically, it's just is a strange thing. So we need to calculate which is the diffusion of the center of mass of the particles in our box. This is the extension to zero temperature of the winding number estimator used for a long time in the path integral Monte Carlo calculation. So the question is that we can access to both things and try to see if we see coherence. Here, for instance, I show what happens in the case between the one-body density matrix, okay, for the stripe and for the crystal. Two interesting things. In the case of the stripe, we calculated the one-body density matrix in the two directions, X and Y, okay? Because we were interested in observing if there is any effect. And the result is probably expected is that we see a kind of plateau. Of course, there is an oscillating behavior because when I move in the from a stripe to stripe, okay, there is this sensitivity, okay, the periodicity of the stripe. But you see that the asymptote is the same in the two directions. So, and this is expected. Why? Because the condensate fraction is the occupation of the zero momentum state, and the zero momentum state is isotropic. Okay, so if there is a condensate fraction, it doesn't matter in which direction I calculate this. Yes. This the density that you have, the density and the tilting angle of your system. So the frequency of the tilts of the stripes is related to the total density of the system. And also the angle, because the angle is a balance between attractive and repulsive terms. Okay, so it's a problem with two variables, the tilting angle and the total density. And if you look at the crystal, so the solid, and you make the same calculation, you see, as expected, an exponential tail. So there is not order in a crystal. Okay, so this is consistent with the idea that the stripes are in reality, in some part at least, super stripes. Let me say super stripes or super solids. It depends on the people. Okay, it's in the sense why I could say super solid, because I have the two ingredients from a microscopic point of view. For me, a super solid is a solid in the sense that you have diagonal order. This is not completely true in stripes, because in the stripes, along the stripe, you don't have this. So there is a one direction in which you don't feel this, but along the other directions, you have spatial order that extends to infinity. This is one property. And the second property is that you have or superfluid density or of diagonal long range order. So if you fill up these two quantities, then for me, this is a super solid. I prefer to say here super stripe because, well, it's a question of terminology. Well, the other thing that we made is to calculate the superfluid fraction, trying to see if the system is really superfluid or not, or when it is superfluid or not. Okay, so here is a plot. It's a bit difficult to see, but here is the total superfluidity of the system. This is density is high. And here I have the superfluidity across the stripes, which is the interesting one, because along the stripe is always superfluid. But the question is if the stripes are coherent along the direction transverse to the stripes. Okay, and we see that the density, the superfluid density is, is a small, but is not zero, and then goes to zero. Okay, so it depending on the density, if the density is too large, I lose the signal. But there is a window close to the phase transition where I see superfluidity. This is also the same for another angle. And how we see superfluidity in our snapshots, this is very nice because we see superfluidity when the chains starts to be connected for long paths. Okay, when the system is not superfluid, I see one particle, another particle, and they are not interchanges, are not connected. Okay, when the system is superfluid, these particles interconnect and finally arrive to a big polymer containing many particles. When you arrive to that and the polymer is of the size of the box, you see superfluidity. Okay, so this is the language that we use in path integral. So this is a symptom here that you accept permutations and the system is no more isolating system. We have studied what happens with this transition because we have the transition from superfluid to normal. Okay, so the idea what you get is then as a function of the temperature, in the case of the stripes, at a given temperature, I have the super stripe. Then at a given temperature, which we call T beta T, the system becomes normal stripe. So the order resists the critical temperature, and then finally arrives to a gas. You lose the structure of the stripes when you increase the temperature just by disorder. In the case of the gas, there is only one transition. The gas is always a gas. and there's this transition BKT. Here I show how the system appears. This picture of the snapshots, I think is quite visual, when you increase the temperature. So you are going from A, B, C, D, increasing the temperature. You see that at low temperature, the stripes are very wide, well-defined, but they are connected. You see paths that connect the different stripes, you see? Sometimes here one, here is another one. When this happens, it means that you are in a super regime. If you increase a bit more the temperature, you look at here, these interchanges practically disappear. There is still one here, but the stripes become isolated. If you increase even more, the stripe starts to be destroyed, and finally you arrive to a gas. So the evolution is here is observed in days of K, as I commented you. So when you are in an ordered system, you have an enormous peak. This is the Bragg peak. But then when you increase the temperature and you arrive to the highest temperature, this yellow, the Bragg peak has disappeared. You have a gas. So some people thought that in the transition temperature, the stripe becomes a gas. This is not correct. So the stripe has a transition, keeping the stripe character from the superfluid to normal. So technically, how is it is made? So because we have been discussing about BKT here, no? How in our numerical studies show that there is a BKT transition. We have two things to do. Of course, first, our system has a finite number of particles. You cannot make 10,000, okay? It's impossible. So the idea is the following. So when it calculates which is the superfluid fraction, okay, as a function of you fix the number of particles, and then you see which is the superfluid, how is the evolution of the superfluid density when you move the temperature, okay? So you calculate at every temperature, which is the superfluid density for a given number of particles. And then you repeat for another number, up to what you can do, which is not much. Then you plot here what is called the universal jump. The universal jump, if the BKT works, is this relation that says that the superfluid fraction depends on the temperature divided by the density by exactly this law. As you see here, we have temperature divided by a density. So this is a line, okay? The line with the slope given by here, okay? So then what you do is to calculate which is the crossing points between our calculation and the universal jump. That would be the estimation of the critical temperature for this number of particles. Then you translate that in this other figure. So you plot for a given angle, for instance, alpha equals 0. You plot these intersections, okay, in this scale, because it is known that the scaling law for the BKT has to be this one from theory, okay? So then if our theory works and we plot the temperature as a function of this inverse of log square, and we see a linear behavior, it means that we have a BKT. This is our language. Okay? If it is not a BKT, you will not see a line in this plot. Okay, because the scaling law would be another one. This is what is called finite size scaling in technical language. Okay, and what we see is that look at here. So the intersection here is the estimation of the critical temperature in the infinite limit. What you see is that when you increase the angle, okay, the critical temperature increases. So this is our prediction. So if the system is just isotropic, is this the critical temperature? But when you increase alpha at a given density, the critical temperature slightly increases. Okay, it seems that the system is more robust against fluctuations when I put this alpha. In the case of stripes, well, I make the same, so the same criteria, the same thing, and I see, as you say, that even in the case of stripes, I see the same scaling, exactly linear with this, okay? So that for us, this is a guarantee that what we have been observing is a Beckett difference transition in all cases. And here you see that from a stripe to a gas, the stripe here is this prediction, and this is the gas. In that case, the critical temperature of the stripe is reduced, so it's not so robust. So depending on the cases. Yeah, well, I have to go fast. Another thing that we have made, have studied extensively, is the case of the bilayer. Okay, the case of the bilayer is geometrically is quite simple. I take two layers separated by a distance h, without tunneling. I put a dipolar gas here, Okay, in that case, all the dipoles are perpendicular to the plane. So in that case, the interaction is fully repulsive at 1/L⁻3. So in every plane, I have just an isotropic interaction. But if you go, as you have particles here and here, you can write the Hamiltonian now in this form. So you have particles up, particles down. This is the kinetic operator for both. I have the interaction intraspecies, up and down, up with that, and down. And then interestingly, I have this up, down, okay? If you calculate which is the interaction between a dipole here and a dipole here, this is a geometrical problem, very simple, because h is fixed. And then as h is fixed, you arrive to this expression that, as you see, if you fix h, this is exactly a two-dimensional problem again, because the only dependence is on the radial distance in some way. So interestingly, very recently, it seems that it could be possible, because what happens with our bilayer is that our distances has to be smaller than probably what can be made in the experiment. Okay, so we need two layers which are extremely close. But now it appears this work by Ketterle's group using this dysprosium, in which they claim that they are able to achieve a sub 50 nanometers. I don't know if this is a lot or not. I am theoretician, but they are able to get this kind of bilayers you see here. Okay, so somehow Lorraine can help to me with this, but this could be promising to get this bilayer in action in the experiments. So about the potential, let me show, this is the up and down, the interaction between the down and up particles. Interestingly, you see, looking at the colors, that there is a conus of attraction. So the particles that are close in the same transverse direction, up and down are attractive, and that's important. Okay, so there is an attraction between this, and there is a conus of attraction, and then becomes repulsive. Okay, so that's interesting, because then it appears that the system is not fully repulsive, but there is an attraction between up and down. And this is the rich system that we need. This is the scattering length that you know that we can calculate both. This is a very technical. Well, the discussion was quite old. The first one is that this potential up-down is a bit singular, because, you know, in 2D, it is known that if the integral of the potential is smaller than 0, you have always a bound state. This is from scattering theory, let me say. But what happens is that if you make this integral for the up-down potential, this is a strictly 0. Okay, so you take this before potential, this one here. Okay, you put this potential, you introduce that in the integral, and you will see that this is 0. So you are in the limiting case. So in the past, there were several papers arguing that there were not any bound state in the system between up and down. Okay, what we have proved, this is not true. So there is always a bound state. Of course, depending on the separation, this could be exponentially small. But if the separation is not large, we have a bound state. And even more controversial was the fact that it could be trimers, tetramers, etc. in the system. Well, this is a bit more technical. So to do the calculation, in this case is DMC, diffusion Monte Carlo. We need a trial function. We construct this as a product of Jastrow terms. I will probably skip that. This is a very technical issue. We need to start our simulation with a given model. We consider equal number of dipoles in each case. And what we see here is a lot of information, but what's interesting to see is that when I put trimers, tetramers, pentamers, hexamers, the binding energy is increasing. So first, the trimers are bound, can be bound. This is the first message, but also tetramers can be bound, pentamers, hexamers, and so on. So the system shows, here is a more detailed plot, that the energy is, the binding energy is increasing. Okay, that was at the beginning for us a surprise because we were not expecting that. Okay, but if you have a many-body system in which the binding energy, the total, is increasing, it means that it could exist a many-body bound state. And a many-body bound state is a liquid, a cell-bound system, okay? That was an initial point that motivated our work. By the way, we also studied a funny situation is that this up and down dipoles is a good representation of a hollow state. I don't know if you are familiar with hollow states. Hollow state is a bound state in which the particles are extremely far. So, okay, so it's in nuclear physics is a very important issue. So we checked that this our system is an example of hollow states with but not with 2 or 3, which more or less are known, but even with pentamers and hexamers. This is very strange. There are not practically any case in nature where the hollow state keeps there when the number of particles grows at least up to 6, like here. That was a real surprise for us. Well, this is the way in which the hollow states are found. So you plot the energy and here the size. So there is a scaling law. And it is, if these curves are above 2, which is this limit here, it is assumed that they are hollow states. In all cases, you can see that they are hollow states. Well, more interesting things that appear in the bilayer is that there are not only, depending on the interdistance, you have not only an atomic phase, but also you have a dimeric phase. So there is a phase in which I have, if you want a molecular state, so up and down form a dimer, okay, and then I have a gas of dimers, okay, because they bound. So I have a molecular state. So we studied that in the past, and we observed that the transition from the atomic to the pair, okay, and then we were able to calculate the condensate fraction of pairs. The condensate fraction of pairs is not estimated with the one-body density matrix, but you need to calculate the two-body density matrix. It's a bit more involved, but we were able to calculate that in the past. But I think, yeah, I don't know. Our last study on this was trying to see if really the system is a liquid or could be a liquid or not. Okay, so I have a bilayer, and I increase the density of every bilayer. So the number of particles up and down is the same. And then I calculate the energy minus the energy of the dimer, because I have dimers, okay? So I have to subtract that. And I look at what emerges. What emerges is the following. For instance, if H is equal 1 in these reduced units, I see what? That the energy grows more or less linearly with the density. When this happens, this is a symptom of a gas phase. Okay, so in the gas phase, the density always grows with the density. But if we move H, curiously increasing a bit, we start to see this figure. Okay, so it seems to be, this is still a gas. It is pointing to like a gas-solid transition, but finally we were not able to find this. But if you arrive to this value, you see clearly that the energy shows a minimum. Okay, when the energy shows a minimum at negative values, this is the key ingredient to say that you have a cell-bound system. So the system at equilibrium, at zero pressure, will be a liquid at this density, which, as you see, extremely small. Again, this is a very, 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 very dilute liquid. Yeah? So here are more cases where we change the different values of H, and you see in all cases, okay, this typical behavior of the liquid. with an equilibrium point and then positive pressure. And what's there here? What's there? This is the spinodal point. You know, in a liquid, I have a smallest density where the system breaks. So we calculated where it is. So in this case, the system is no more homogeneous and breaks in drops. This is the spinodal decomposition because it's negative pressure. Remember, below the equilibrium density, where the minimum you have negative pressures. Above, you have positive pressures. You can stress the system for a while at negative pressure, but finally it breaks. When it breaks, is the spinodal point. Okay, so this is the negative part. So and this is more or less the phase diagram that we published. So we have here the formation of droplets, but then at a given density, it appears clearly liquid. Okay, so our idea is that that could be an alternative to the, you know, these drops in the Bose case announced by Petrov, in which you have this, you have two bosons with an attractive interaction between bosons A and B, and finally form a liquid. Okay, in that case, it would be interesting because all the atoms are the same, so they are just, for instance, dysprosium, or I don't know, you put in a bilayer, and you are able to found any body-bound state, which is exceptionally ultra dilute. It's very, very dilute. And that would be interesting to explore somehow with this finding by Ketterle would be doable. I don't know. Well, this is also the condensate fraction that we calculated, and well, it follows more or less the same. When the density grows, it goes to 0. So it is consistent. It's also consistent, the excitation spectrum as a function of the energy, sorry, as a function of polarization. So if you change the balance between A and B, okay, that's important because at the beginning we're equal. But if you play to change NA and NB, such a way that the sum is the same, so you can distinguish if you have a molecular condensate, a molecular system, or an atomic system. The difference is that when you have an atomic system, the energy as a function of this polarization grows quadratically with the polarization. And here it appears the susceptibility, okay? But a spin susceptibility. When you have a molecular condensate, as you have a bound state, so the energy grows linearly with the polarization. And you can distinguish by calculating the energy. If you have a molecular gas, in a molecular gas, you have these dimers, and the energy grows linearly with the polarization. That's funny. Huh? But when you have a liquid or an atomic gas, you see this is quadratic, which is normally and what happens if you don't have dimers. And this is new, still unpublished. What happens when instead of a bilayer, I have a multi-layer? Imagine that you can manage to put 2, 3, 4, 5 layers, okay, with the same terminology. Well, what happens in that case is that it's interesting because you can evolve from a gas to a crystal. So you are able to see, look at here, you see a kind of triangular crystal. You can identify, no? The triangular geometry, okay? So it means that the atoms in the multi-layers are so attractive, okay, that they are frozen in a kind of line, and these lines form a triangular lattice. So in fact, they are crystals, okay? But crystals extremely dilute, okay, again. So we have another realization of, we have crystals of droplets, okay? But in that case, will be crystals of arrays of dipolar atoms. Okay, that's interesting. And we are writing now this paper. We have evolutions from a gas to a crystal, and it's interesting also that we have found that a new phase in which this I don't know how we call this. So instead of having the line, so the line could bend. Okay, so they want to be in the line, but they fluctuate quite a lot. So, and then you are not able, you see that the system is not a gas. This is a classical gas. You see some order, but not a crystalline order. It's like there is some bending of these structures, okay? So this is a bit difficult to find. This is gas of change. We have called gas of change. Would be interesting to know if it could be observed in experiments. I don't know how much time I have. 1 minute. Wow, sure. Well, just quick. I also worked for many years in helium. I was involved in the history of Moses Chan, and I remember that was a big exciting about the supersolid stuff in helium. For 5 years, we were, everyone in our field was trying to find, but then was not possible to be confirmed by the experiment. But we are continuing to explore helium. For instance, I just comment that you take graphite and then you put helium on top, and helium is strongly absorbed on graphite. This is known from experiments from all. So, and then what happens is that you have layering transitions. So I have a first layer. This is very funny, and I put more helium, and boop, at the moment it appears the second layer. You put more, and then boop, third layer. So the system has first order layering transitions, and very clean. There is not any other system in nature showing this with the clarity that you get in helium. Well, we explore it a lot, but what we find is that in the second layer of helium on top of graphite, we observed that there is one of the registered phases. This is a very technical, but when helium atoms are located in a positions commensurate with the lattice, which is essentially graphene, there are several structures, okay, geometrically possible. One of them is the 712, okay, which is technical. And we see that in that case, this is the estimator of the superfluid fraction. We observed not zero signal, okay? So it means that is a crystal, so the particles are localized, but they show some small superfluidity. That was quite discussed, but we were happy because after a while of our publication, so the Kim was one of the involved, Moses Kim Chan were the authors of the famous paper, but Kim still is working on this supersolidity in helium, and they found this part here in the second layer, exactly the second layer that we were studying, where they claim they were not sure about if it is a registered phase or not, but that they were able to see a superfluid here, which is exactly at the density of the 712. So probably there are some phases in helium absorbed on this graphite, which are supersolids. By the way, this is not the supersolid that we were searching for, okay? Because the supersolid that we are searching for is because the system breaks the symmetry spontaneously. And this is induced by the substrate, okay? So this is not really the true supersolid, the Sangreal, so, okay? So, but well, it's still interesting to show. Well, the remarks, I think with this I will conclude. So we observe this 2D geometries, is very rich system in 2D, because you can see the formation of stripe phases. These stripe show superfluidity, in this sense are supersolids. And especially we're excited about these multi-layer geometries, if they can be made in the experiment. And I think we are promising to get these liquids and even the solids using ultra-cold Bose atoms. And with that, I think I arrived to my time. So, good job. So thank you for your attention. Thank you.
So we have time for a few questions.
So I want to ask about the BKT transition.
Yes.
If you have dipoles, then in the 2-dimension, you have an anisotropy.
Yes.
And this means you have 2 different superfluid densities.
Yes.
How do you take into account this fact in your numerical estimate?
Yeah, because what we scale is the total superfluid density. Okay, so we have 2 components of the superfluidity along the stripes and across the stripes. Okay, but the system is this. So we compute the total superfluid density. What we scaled with the BKT was the total superfluid density. Okay. It changes. It changes of size, but the scenario, so the scaling that we observe, the scaling is the same that the BKT. So if you look at, for instance,
I mean, the straight line you have plotted, right? That was a standard straight line without this anisotropy.
let me show here, for instance, you have both a gas and a stripe here, okay? And both cases, we scale the total superfluid density. And in both cases, we see a linear dependence. Because here was a debate about if the superfluidity would be one-dimensional, okay? So if the system would be a transition one-dimensional because the stripes are like a one-dimensional systems. But if you try to scale your results with one-dimensional scaling, it doesn't work. So we tried, and the paper is discussed. So the 1D does not reproduce the data. So that is not scaling. So here you see linear behavior. Linear behavior with this scale, it means BKT in our language. Yeah.
About the stripes, I noticed that your Hamiltonian only has the dipole interaction. There's no S-wave part.
No.
Like a contact.
Yes.
If you were to put a repulsive contact, that would help with the collapse.
Yes,
I guess.
Would
that spoil your stripes?
No, I don't think so. No. What happens, and in fact, we have some results not published that we have put this short range part, and you see that the stripes keep there. Of course, are even more stable because I can cross, I can cross the line, and then I see. Even if I can show you, we have extended, in fact, our calculations to 3D. I don't know, I have some results. So this is the results in 3D where I have to put the short range. If not, it collapses. And in the 3D, this is how our evolution evolves. This is similar to what Lorian has shown in the Innsbruck experiments. No, changing the scattering lead, the system evolved from a gas, just one drop. It appears to drops. They seems that they communicate, and finally they are isolated. So, and what's nice in our case is that we can calculate both the static structure factor and the one-body density matrix. So, if we will have peaks, for instance, this case, or this case is more clear. I have one peak here, which is corresponding to the formation of two drops. And I see a plateau in the one body. It means that the system is super solid. Okay, but in that case, you are right. I need to put the short range part, otherwise it collapses.
Thank you.
Maybe I can just make one question in between. So now you find the supersolid only at high density.
At high density, yes.
Yeah. And if you would like to compare to experiment, instead you would like to go to a regime where the dipolar and the contact compete roughly on the same order and go to low density.
Yeah.
Do you expect something different?
Yes. So in the diagram, in the phase diagram, what we see is that if we put the two body part, the transition moves to the left. So you can get stripes at much lower density. Okay, I don't know, am I explaining correctly? Sorry, here. So what we see is that this line, this phase line moves to the left, okay? So in this sense, we were more accessible to the density, but still.
But you would have to go back to 0.01.
Yeah, we need, no, for the moment, it seems difficult to get this. I'm sorry.
So it seems like a superconductor would be different in the sense that there's no shades of superconductivity. It's either a superconductor or it's not. And so if you're looking in quantum Monte Carlo, can you see when something becomes a superconductor?
Well, for me, superconducting means superfluidity with charges, okay? So we need to put a charge system, for instance, electrons, but electrons are Coulomb particles, and that's a bit more tricky. I am not sure.
Yeah, so just from an experimental impression, is there is there a superconductor? Is the direction across or along the stripes more favored for superconductivity?
Along the stripe is clearly favorable because along the stripes,
Okay.
okay, you have a gas if you want. It will be a gas of electrons. Okay. The question is what happens in the transverse direction.
Exactly.
That I think is the interesting study. So because the communication between the stripes, as it happens also in the drops, is very tiny. So I don't know if we would resist because rapidly the system becomes to be isolated. So insulating, yeah. Sorry for the bad news, but
just one question. What is the tilt angle for the stripes to appear?
the stripe here is the alpha. So you can see the phase diagram here of the stripes. You can identify between 0.5 and 0.6 and the range of densities that you
So
have
if
here.
the dipoles are polarized perpendicular to the plane, there are no.
There are no stripes, not at all.
And horizontal, there'll be stripes, no? In the
To
plane.
have stripes, you need anisotropy. Okay, so it's fundamental. If not, if you don't have anisotropy, the system is poorly repulsive. 1 over R to the 3 is just a gas that becomes a crystal at high density, and that's all. So the anisotropy is crucial to get the drops in the 3D and the stripes in 2D. For me, it's very similar. The stripes and the drops are of the same origin.
What determines the direction of stripe? What determines the direction of stripe?
Well, you are in a plane, so
It's XY plane, but
yeah. So essentially, you have 2 directions, and then are degenerate. No, so this one and this one. In this case, is where it is more attractive, and this is more repulsive. So the system organizes in stripes following the more attractive part, which in our case is the y-axis. Yeah.
Thank you very much. I have a final question regarding the bilayer case.
Yeah.
So imagine a situation in which one of the layers isolated tends to form a crystal, for example, with a certain periodicity. And then you choose the periodicity period, the period of this crystallization to be irrational between the 2 ones. So if you couple them together, then there's a competition between 2 crystallization periods that is irrational. So in principle, you could go towards a quasi-crystal or something like that. Is it possible?
In imagination, yes, but the problem is that in a single layer, it's hard to have a crystal. I need to go to very high density. If I take a layer, I need to go to a density extremely more than 200 in these units to crystallize, which is a regime in which obviously we are very far from what is interesting. Theoretically, we can go to, but yeah, sometimes our ideas from theory are not approaching the ones from experiments. So we live in another world sometimes, no? So theoreticians work in, I don't know, we search for beautiful things, but then it happens that are not doable. In that case of the bilayer, multi-layer, it seems that now could be possible in bilayer, but probably they can make more than a bilayer, I think so. Yes.
Hi, in the case of the helium on graphite,
yes,
in the second layer, how do you know that it's a solid and not a liquid that is there?
Well, good question. In that case, what we make to decide the phases is to repeat calculations using a translational invariant wave function. Okay, you use a Jastrow normal without localizations. And then you calculate also with one with putting the particles in the points where the crystal will form. And then you compare the energies. So you calculate with 2 symmetries and you decide which symmetry is the best according to the minimum energy. Because you are at 0 temperature, there is no entropy here.
Okay, I see no urgent question, and for sake of time, I think it's a good time to make a break, and we start in also 20 minutes or so. Yeah, thanks
Thank
again.
you.
So at 3. don't know. Can you try?
Hello,
Did you move this? I don't know.
hello.
I think, did you move this?
No, I did not do anything. Oh.
Yeah.
Yeah, hello. It's okay. Now it is on.
Okay, good. I propose that we start again. So the last talk for today is from Sadhan Adhikari on supersolid formation in a Bose-Einstein condensate.
Thank you very much. First, I thank the organizers for inviting me and organizing such a beautiful conference where so many speakers talked about many different topics of cold atom physics, and especially supersolid. There are several talks before mine on supersolids. So I'll talk from a different point of view. There are talks on experiments and exact Monte Carlo type calculations, but I will talk from a different approach, mean field calculations of the same thing about mean field calculations. I am from the Institute of Theoretical Physics of the State University of Sao Paulo. And this is a symbol, and it's a funding from CNPq. And physically, our institute was located in this place till about 2009. And then we moved out of this place. This place belonged to the Foundation of Institute of Theoretical Physics, and they administered this place, and we moved out in a different campus. So this place, I am familiar with this place, and I'll talk about my collaborators on these things. This is Luis Yang Silva. He is from University of Cartagena, Colombia, and two collaborators from India. This is Sandeep Gautam. He's a long-time collaborator on dipolar BEC with me, and a PhD student who works with Sandeep Gautam. It's not going. Oh, now you have seen that what is supersolid. Supersolid has a properties of both superfluid and crystalline solid. Superfluid, it flows without friction. That's a simple property. It has a phase coherence. And if it is a crystalline solid, it does not have continuum translational symmetry. It is broken. It has discrete translational symmetry, and you have at the same time breaking up gauge symmetry, continuum gauge symmetry, because of the generation of the phase coherence. And this was observed experimentally, a superfluid, in two cases. So a crystalline structure, and most of the experiments, they tried to also verify if there is superfluidity, and if the crystalline structure is rigid, that doesn't easily break. It was observed in dipolar Bose-Einstein condensate, and also spin orbit coupled SOC spin half BEC. So in trapped dipolar Bose-Einstein condensate, it is possible to have square, triangular, and honeycomb lattice and other symmetries also. But experimentally, the preliminary pictures, they showed mostly the triangular or hexagonal symmetry. And trapped and uniform spin half, spin 1, and spin 2, and even spin 3 systems, they show different types of symmetries. So apart from mean field calculation, you can do theoretical calculations, sometimes using variational approach, and sometimes using the solution of the problem with no nonlinearity, solution of the homogeneous problem. And from those solutions, you can construct these symmetries. And we'll talk about future experimental possibilities. A supersolid is a quantum object which is periodic and ordered, spatially ordered, stable structure as a solid crystal that can flow without friction. This concept was suggested by many authors. It has been shown by previous speakers, but it gained more impact, more attention after the work of Henri van Lifshitz, and after that, many years passed, and only recently we have seen the experimentally some signs of supersolidity. Supersolid. And what is the idea of Henri van Lifshitz? He said, usually the supersolid is you have to create a modulation in the density. Like you have to arrange certain amount of particles or entity in one place and another place. Usually ground state of any system is uniform. The ground state of the harmonic oscillator problem, this has no structure. First excited state, you have some structure, and you have to go higher and higher in the excited states to create structure in the density. And so you need some density to create this, some energy to create this. So at some critical wavelength, you see as the wavelength of the modulation decreases, you have less and less things, the energy is less. And if the wavelength of modulation decreases, you need make excitation, you need more energy. So some energy is needed. So Henri van Lifshitz, they argued that if the temperature was cold enough, this energy in some system could be typically zero. And then the system will spontaneously form a periodic modulation in density at this wavelength. So that is the idea. So there is a small difference between supersolid and crystal in mean field approach. A crystal is a spatially periodic arrangement of atoms, but supersolid is which we will observe a spatially periodic phase coherent arrangement of small droplets, each containing many thousands of atoms, maybe molecules. Because of phase coherence, a supersolid is expected to be able to move without deformation. Something like should be able to move. But if it is in a trapped system, there are other ways to check this movement in case of mean field calculation. And 2004, some group, Kim and Chen, they published a paper where they reported supersolidity of helium-4, but which could not be repeated, maybe because of some experimental error or other thing. And some groups are working in this direction, but the possibility of finding a supersolid helium-4 seems remote. But it's not excluded. It's possible that there could be supersolidity in liquid helium-4. So these are the two papers. The first paper showed the supersolidity, and second paper contested it. So supersolidity and dipolar BEC. In 2019, in different experiments, 3 groups led by these 3 groups, Francesca Ferlaino, Modugno, and Tillman Fau, they observed supersolidity in a quasi-1D dipolar system. And in 2021, the same group, the Ferlaino group, observed a quasi-2D dipolar supersolid with hexagonal symmetry. And these are the references of those. papers, 4 papers. And supersolidity in a spin orbit coupled BSC. I'll talk about what is a spin orbit coupled BSC, because in a normal atom, the electrons have charge. So electron associated with the charge as it moves in an orbit, it has angular momentum and it generates a magnetic moment. And that interacts with the magnetic moment of spin degree of freedom. So it makes the L dot S coupling. But we'll see that this spin orbit coupled BEC, that is in case of atoms, the atoms do not have charge, but when they move, it is possible to create a coupling between the motion and the spin degree of freedom. We'll see how it is done. And in these 2 experiments, they observed supersolidity in spin orbit coupled BEC. So we'll report some of our studies of new results on supersolid, the partially periodic superfluid states in quasi 2D dipolar BEC and quasi 2D spin 1 and spin 2 spin orbit coupled BEC. So spontaneous periodic structure in a dipolar BEC. One can have a spatially periodic structure in the trapped quasi 1D and quasi 2D dipolar BEC. It can be shown in, it was shown in experiment, and also it can be shown in theoretical calculations. The experimentally observed was the linear and hexagonal lattice structure, but theoretically we can predict other structures also, square, honeycomb lattice in quasi 2D dipolar BEC, and also in spin orbit coupled BEC. And rectangular orbit lattice, these are also possible in dipolar BEC. Now let us talk about a little bit about the dipolar BEC. It's a very simple thing. The dipole moment of these are the atoms which were normally used in experiments, dipolar experiments, and they have a large dipolar moment compared to the rubidium atom or other atoms, alkali metal atoms, which has 1 unit of Bohr magneton, this dipole moment. For some reason, the nature is not so symmetric. So these other atoms have many unpaired electrons, and so they have large dipole moment. And dipole moment is a measure of this dipole moment is the dipole length, which is used in most of the calculations. You have seen this. This is the measure of the interaction strength, dipolar interaction strength. So you can have this dipolar interaction, it's angle-dependent interaction. You can have an arbitrary reaction to dipoles. It's like tiny magnets. You can have them this way, or this way, or this way. So this is called, if this is oriented in a plane, in a line, it will form a cigar shape. It is attraction between the north and south poles of the magnet, because each atom acts like a tiny magnet. And if it is disc-shaped, it stays like this, and there will be repulsion. In this case, there will be repulsion between different atoms, the dipolar interaction. And this is the static dipole-dipole interaction. There are two possibilities. One is the magnetic dipole-dipole interaction between these atoms. Also, you can have between molecules the electrostatic dipole-dipole interaction. This is electric and magnetic. So the important thing is that if the 2 dipoles are oriented like this, it is stable and attractive, favorable, and this is unfavorable. And this is the interaction potential. You see, if you have a dipolar BEC, and if you increase the dipolar moment, relative dipolar moment, by controlling the contact interaction. There is always a repulsive contact interaction. If you reduce that, the dipole interaction increases, and then the condensate becomes elongated in the direction of dipole moment. So atomic dipolar B is a short-range contact interaction controlled by atomic scattering length, and long-range dipolar interaction controlled by ADD. The ratio between the two gives this, and this determines many property, the epsilon DD of this system. So one interesting thing is the matter in bulk is stable because of short-range repulsion and in nuclear, atomic, molecular physics, and long-range attraction, which makes the thing stable, matter stable. So dipolar interaction usually makes a stable dipolar system. But the trouble is that the dipolar interaction is not attractive in all directions. And because of this, the mean field theory leads to collapse instability, collapse for any trap and for any number of atoms for a sufficiently strong dipolar interaction. So dipolar droplet, this was seen first in this experiment in 2016. In this classical experiment, they observed that there is spontaneous transition from an unstructured superfluid to an ordered arrangement of droplets in a quasi 2D dipolar BEC in the collapse region where there is would be expected collapse. What is the collapse region? If you solve the Grosspitaevsky equation, because here people showed this equation, and this is for dysprosium, and this is the scattering length, which can be varied by phase-back resonance. And this is the experimental value of scattering length. And this is the EDD, that parameter I showed. The region below this green line is this collapse region. So but this way, this is the number of atoms, and this is the scattering length. But in that experiment, it was seen that in this region, you have droplet formation. But usually the Grosspitaevsky equation will show collapse in this region. So this is the mean field collapse region. So later on, this experiment was repeated. Now this is This is the result of that experiment. The experiment showed this kind of droplets in that. But at that time, and they showed something, generation of something like 10 droplets. There are 10. But in this problem, in this paper, they did not care about supersolidity. They are more surprised because of this drew a lot of attention because the system did not collapse but formed droplets. And these droplets typically had some 10,000 atoms, something like that. So dipolar BEC is stabilized by beyond Mill field correction because Grosspitaevsky equation is true in the very weak coupling limit when the gas parameter A times scattering length times density to the power 1/3 is very small. But if it is large, then other higher order quantum corrections are important. And one of these lowest quantum correction was calculated by Li Huang Yang long time back in 1960s. And this is repulsive, strongly repulsive. So it can at short distance and it can stop the collapse. So that's why the collapse is stopped. But if the number of atoms go beyond certain size in that trap, it again collapses, but the stable position is formation of two droplets and not a very large droplet. So that's why they break and try to arrange on a lattice. In all problems, all studies here, the dipole moment is perpendicular to the plane of the lattice, always. So in the plane of the lattice, where the lattice is formed, this one, this plane, these droplets are repulsive. So they stay apart and the trap keeps them together. So this is the 1D trap. If the trap is 1D, 3 experiments, they showed that there is formation of droplets along a line. And 4 or 5 droplets are seen at that time. And this is the result of one of the experiments. This paper, 2019, 3 papers were published in 2019. So if you expand and if you plot the linear density, it is like this, 3 droplets, 3 droplets. And once it is large, they separate. You can really see after expansion, 3 droplets separated. And this is the result of the 2D trap work in 2021. So you can have 3 droplets in a line to 7, the hexagonal lattice in a 2D shaped trap. So this is the Grosbeck-Typesky equation that we'll be using for the calculation. The first line is known to everybody. This is the simple equation. And the second line, this puts the dipolar interaction. That interaction here, UDD is the dipolar interaction. And this is the correction, higher order correction due to Li Huang Yang. And for the stationary state, you have this Hamiltonian equal to mu times psi. And this is a trap. And this is the dipole length of the system. So what is the modified Li Huang Yang interaction due to Professor Pelster and Lima? This is the original coefficient that was attributed to this term gamma LHY. And the correction for dipolar thing is this. This is this. And this integral, this goes to 1 when the dipole epsilon dd is 0, no dipole moment. And this is the integral. This integral can be worked out this way, and E is this. So we'll be using this for our calculation, this model. Once we make this model, this is the model, it becomes different from experiment and reality. So whatever you will see after this is a result of this model calculation. And this is the energy of that system. This is the energy of that system for that model. So I'll be talking about the 2D trap mostly, a numerical simulation with dysprosium atoms. ADD is this, and A experimentally is this. A smaller A facilitates the formation of droplets. You have seen that the collapse region in that figure is here down below. An experiment marginally touches the collapse region, this experiment. So it will be better to keep it here where it goes well into the collapse region. So you can use the phase-back resonance to take the scattering length at 85. In some other values, this study was 88 was used. And results of calculation, we'll solve 3-dimensional Grosbeck-Typesky equation. Is solved by Frank-Nicholson method, and we published these programs to be used in this solution. And the harmonic traps, we'll be using 3 harmonic traps. Omega x will be taken always 33 and 167 hertz. And we'll be using a quasi 1D trap with omega y with 110 and a mixed trap medium, which is omega y equals 60 hertz. And a third trap is quasi 2D, it's 33. But in the experiment, the omega x and omega y are not identical, but we'll take them identical. So you see that if you multiply wx, wy, wz, this trap is strong, strongest. This is mixed, this is medium, but it is between 1D and 2D, and this is 2D, and this is the weakest trap. Let's see some results. We have 25,000 atoms, and this is the 1D trap. 1D is the top trap. This is the strongest trap. So you have 3 droplets. Then this is the mixed trap, which is weaker, the second trap, which is medium. It's not so strong. So you see only 1 droplet is formed. Because the first trap is very strong, so it is crushed in the middle and 3 droplets are formed. Now it is 1 droplet formed. And then you go to the 2D trap. And 2D trap, no droplet is formed because it's at this stage weak enough for the system to make collapse and form droplets. But if you take more atoms, it forms a droplet. Now we increase the number of atoms. This, you see, this is 25,000 atoms, 25,000, 25,000, and this is 40,000. If you increase the number of atoms, 70,000, you have more droplets. Because the stable situation will be forming more droplets, and they separate due to repulsion in that plane. Because the dipole moment is always perpendicular to this plane. And now you take a weaker droplet, weaker, this is the mixed, trap, which is neither strongly 1D nor strongly 2D. So some droplets go in the other direction. And this is the 2D trap. So it is more symmetric. And if you increase the number of atoms in the 2D trap, it makes more droplets. Finally, we have increase the number of atoms further, you have more droplets. And if you come to the middle droplet, some droplets go outside. And this is the 2D plane, so it's more symmetric. And this is still 2D plane. But you will see one thing. Here we showed a square lattice symmetry. Here is a triangular lattice symmetry. This is, we are presenting this result, but here also we can have the triangular lattice symmetry, and here also the square lattice symmetry. You will see that. So first we show the results of square lattice symmetry. This is number of atoms, and this is always now quasi 2D trap, the weakest trap, which is the X and Y plane. The frequency of trapping is 33, and in the Z direction is 167. So these are the symmetric, parity symmetric states. You have a maximum in the center. So 3 by 3, 5 by 5, and 7 by 7. And now this is parity antisymmetric state when there's 0 at the center, 2 by 2, 4 by 4, and 6 by 6. But say in the same trap, you can have the hexagonal lattice, or you can have honeycomb lattice, something like this. Energies are quite similar. But how a 3-dimensional isosurface of these things, this is the square lattice. This is honeycomb lattice, and this is hexagonal lattice. So now it's xy and z is the perpendicular plane. Previously, we are observing a section of this in the xy plane. But what is the universality in there? But now I make some comments. But how could I generate all the three different types of lattice? Sometimes I give as the initial state a uniform a ball means spherical spherically or circularly symmetric state, and it breaks during numerical iteration, and it forms droplets, and that somehow goes to one of the final solutions. But I can also give an initial state which is like this, or which has a hexagonal structure. I give one state with 1, 2, 3, 4, 5, 6, 7 initials, this one, and increase the number of atoms. Then it forms more droplets outside and stays in the hexagonal thing. And similarly, if I give as the initial state, some state of square lattice symmetry, it goes to the square lattice state usually. So sometimes it goes to a non-periodic state also. There is a question, is it always periodic? No, it is not always periodic. But sometimes it goes to a non-periodic state, many droplets. So, but interesting thing, the universality of this is the energy. So there's a fitting, straight line fitting here, and green is this square is square lattice states, triangular lattice states, honeycomb lattice states, and these are mixed, which are nothing, neither this, neither that. And this is for that trap, the droplets are formed around 33,000 atoms. And this is the region where there are no droplets. So this is ordinary BEC that follows that thing. And these are the energy of droplet. These few circles are taken from another paper, 39, a paper by Blackie from New Zealand. He had a very strong trap and strong attraction. So the droplets are formed at small values of atom number, each droplet containing small number of atoms. Compared to this is the number of atoms, this is energy, N is the number of atoms. But what is interesting that it follows the same line. And this is the number of droplet which increases with the number of atoms. So this scaling is like this. It is different from Thomas Fermi scaling, Thomas Fermi energy. This has a scaling, and number of droplet was like this. And this includes all types of symmetries. But trouble with a harmonic trap. The harmonic trap makes the formation of large supersolid lattice very difficult and generates intense background atom cloud many times. So you will see that there is red cloud here around these things. And this can be reduced by taking in case of a box trap. So I give some result of the box trap. The droplets are, there is a box trap at the boundary, and I form these droplets. But will you ask, did I put this thing as initial state? No. I put such a thing as initial state, but it rearranged in this fashion. And these states are probably for that separation of box trap. We take the wave function 0 at the boundary of the box. The box size is given in each case. So it is very very robust, because it changed from this setting to this. I never thought about this setting. Now the experimental possibilities, I had some comment. In 1D experiment, only few droplets, maybe always less than around 8-10 droplets in 1 or 2D setting was found. Huge lattice is possible in theoretical model with Grosbeck-Taipsi and Li Huang-Yang correction. Valid in, but this correction, this Hamiltonian is valid only in the weak coupling limit of this. A is the scattering length, this is the density to the power 1/3 less than 1. So experiment will be guided by the quantum mechanics and not by the theoretical model. So collapsed droplets have high density and we are moving away from the weak coupling limit. So higher order terms would be important, and we have to correctly sum a slowly convergent or even divergent series of corrections. So careful experiments are called for to see if a large supersolid can be formed in this model. But I believe that the Li Huang correction, which is valid in the weak coupling limit, and we are using it in a relatively stronger coupling limit, and it is generating too much repulsion in the theoretical model. And because of that large repulsion, the system cannot collapse and we form a big droplet lattice. And that repulsion should be somehow attenuated, somehow reduced. And in that case, so many droplets will not be formed. So this, we published these papers on this. So let us talk about a little bit different problems: spontaneous periodic structure and spin orbit coupled SOC BAC. One can have a spatial periodic structure in component and total density of a spin orbit coupled BEC, both trapped and untrapped. Pseudo spin half, hyperspin 1, hyperspin 2, hyperspin 3, spin or BECs have been used. So experimentally observed, this stripe has been found in pseudo spin half spin orbit coupled BEC. Theoretically predicted as stripe structure, square lattice structure, and triangular lattice structure in spin 1 and spin 2 BEC. There are some paper by other group in spin 3 BEC where they found some other exotic structure. So what is spin angular momentum in an atom? This is sigma dot L, the spin dot L is R cross P. This coupling between spin and momentum naturally arises due to the charge of the electron. So you have two magnetic moments, they interact. But atoms in a BEC, atom in a BEC does not have charge, and this coupling is not possible. Instead, a different coupling between the spin and momentum is engineered in a BEC, will be introduced in a BEC. So we see that a Zeeman interaction is typically represented by mu dot B, and mu is sigma is a spin proportional to spin dot B. So now you'd have a static electric field, put the atom in a static electric field, simplest model. In the lab frame, it generates a magnetic field B in the frame of the moving atom with momentum K. This is just giving a Lorentz transformation to the F mu nu operator that will show the, F mu nu tensor. It will mix the electric and magnetic field, and if you take a pure electric field, this will generate a magnetic field. And once it generates a magnetic field, this is an external electric field. Once it generates a magnetic field, this term will generate this kind of interaction. So it generates a coupling between spin and motion of the atom. And this coupling is known as, exactly this form of coupling is known as the Rashba spin orbit coupling. But this is not spin orbital angular momentum coupling, but this is a coupling between spin and momentum. It's different from S dot L coupling. It has spin-or interaction. A spin-orbit coupled BEC has spin-or interaction and spin-orbit coupling interaction. Spin-orbit coupling interaction is this. For simplicity, we'll consider the spin-orbit couple SOC, the spin-orbit coupling interaction, and no spin-or interaction. So we'll have a BEC of different components with no spin-or interaction. The spin-or interaction can be removed by adjusting the different scattering length because now there are 3 components or 5 components of BEC. So in 3 components, you will have the different scattering lengths in spin 0, spin 1, spin 2, this kind of things. Whereas in a scalar BEC, you have 1 scattering length. You have many scattering lengths here. And somehow, if you tune by phase back resonance the scattering lengths to be equal, you can eliminate the spin-or interaction. We did the calculation with spin-or interaction and without spin-or interaction. So here I am presenting results of the without spin-or interaction because that's simple. So you have seen those are the sigma x, sigma y, sigma z. This is sigma x and sigma y. For this is spin 1, this is spin 2. So the equations, the Grosby-type equations, it has this form. So there are 3 components now. Spin 1, hyperpoint state, this spin +1 component, spin -1 component, spin 0 component. These are the spin orbit coupled terms, which come from the Rashba spin orbit coupling. The spin matrix coupled to the momentum. And these are the derivatives of the space. D plus minus dx, this, dy, dx is this, dy is this, dt is this. And here the nonlinearity is the total nonlinearity of the 3 components. So we have only 1 scattering length, A0, the spin 0, and the other scattering length is made equal to this by a phase back resonance, we assume, and then the spin-or interaction goes away. N is the total density, like this, and it has 3 components. And C0 is the nonlinearity, this nonlinearity. And spin 2 is technically more complicated, but it's a similar set of equations. Spin 2 BEC. Now we'll show some results. And again, we can calculate the energy. But it's again, as in a Grosby-Typesky equation, but it's technical thing. The 2-dimensional, we'll solve the 2-dimensional spin orbit coupled GP equation and numerically again by this, and these are the programs which are published in these papers. Supersolid formation is possible in both trapped and untrapped systems. Well, about the theoretical part, theoretical foundation, we did I forgot to tell, did not bring, the supersolid dipolar system. We can do the variational calculation by putting for small system, putting the droplets in arrays and minimize the energy. And here we can do a theoretical calculation by solving the linear problem. This problem is just putting the nonlinearity to 0. And they show the same structure. And now spin 1 and spin 2, we are talking about soliton, free system. So you have to have the nonlinearity, negative nonlinearity large, so that a soliton or bound state is formed. And this is the collapse region, like a scalar BEC. And this gamma is the strength of the spin orbit coupling interaction. So there are some results, the strength of the spin orbit coupling interaction, and the C0 was fixed. It's not changed from figure to figure. C0 is fixed to something like minus 0.5. So these are the results which show has some vortex and so on. This radially periodic. These are not really supersolid states, but this comes out from the solution of the linear equation also. And these are the states. This is a asymmetric state, and these are the stripe states that come for gamma equal to 4 in spin 1 system, and C0 is minus 0.6. And these are the, you see the two-dimensional square lattice. These are the two components. Here there is no asymmetry, and the plus spin half, plus 1 spin component and minus 1 spin component, they are same density, and this is the spin 0 component, and this is the total density of the 3 components. You see there is structure, square lattice structure present. And if you go to a higher spin, gamma equal to 8, this square lattice, this stripe structure survives in the total density. Same result, similar result for spin 2. We have a vortex at the center, symmetric case, +2, -2 for plus minus, and this is plus minus 1, and there is no vortex, and total density, there is no structure. So there is only radially periodic structure. But for gamma equal to 1, you can have a triangular lattice. This is spin 2 system. And C0 is, I think, -1. This is spin 2 system. You have this triangular lattice structure, which was absent in spin 1 and also through spin half. But also you can have square lattice structure like this and stripes. Again, there is no stripe here in the total density, but the stripe will appear in this total density as gamma is increased. I didn't show the result. And here is some plot of energy. Of different types of states, square lattice, this vortex states, asymmetric states, stripe states, this is the energy. And these results are published in these papers. Here we have the full spinor interaction for spin 1. We have full spinor interaction for spin 2. Here, so this has ferromagnetic, paramagnetic states, and here you have ferromagnetic, paramagnetic, and cyclic states. Higher up you go in spin, like spin 3, they have other magnetic states. And this is without magnetism, making all with no spin or interaction. So different spatially periodic structures are possible in different BEC. Apart from new experiments and theoretical studies to find these stationary structures, one could consider studies in dynamics to test the superfluidity and rigidity. On the present stage of experimental SOC BEC seems to be difficult. Theoretical studies of this may reveal the supersolidity in general. The experiment on SOC BEC that showed supersolidity, that was in a quasi 1D trap, and these are 2D, which is more complicated technically. So thank you for the attention.
Thank you very much. So we have some time for questions.
Right.
Do you have any indication if these structures are super solid or just solids?
Which one?
All these structures of the droplets?
All these should be supersolids because they are phase coherent.
But how you show the phase coherence?
Because it's solved by the mean field equation.
I think it's not enough.
But we also studied dynamics. Dynamics one is oscillation, it does not change, shape, and also angular oscillation.
It's a bit.
That is the experimental test.
Yeah.
For no, yes,
For me, it's not fully convincing. Thank
of
No,
course
I
not.
think
But
you need to add some noise, but I think at this scattering length from the structure that you show, I would not say that it's super solid.
say it again.
You will need to add some noise into your simulation, no?
Yes.
Yes.
Did noise,
do
but
it?
it's oscillation, angular oscillation.
Yes.
We did. For one dimensional, it's perfect. It oscillates. And Caesar mode oscillation. Caesar mode oscillation is that you have an asymmetric trap in the XY plane. So if you give a rotation, it starts oscillating.
Yeah, I don't know. I would
This
say
is
also from the density.
No,
for
it
five
is
and
always
12.
there. The noise is always there. It's full of noise. It's real-time simulation we have done, and it's full of noise.
Mhm.
Like in experiment, you have a lot of noise, and this in numerical real-time simulation also there is noise. They're stable.
Can I ask also one question on
Yes.
this flat, like the flat traps, like uniform traps?
Uniform traps, yes.
Simulation. So what are the boundary conditions that you used?
This uniform trap is
No,
a
but the one
periodic
with-
boundary condition. Periodic boundary condition. There is no end.
Okay.
There's no end. This is not a real soliton because it cannot move because of the spin orbit coupling, but its stationary state, it extends to a long distance, and there's no end of the calculation. So periodic boundary condition again.
No, I meant actually for the dipolar case, but I guess it's the same.
Dipolar is not soliton.
No, I mean the flat, you had the uniform traps. Oh,
And dipolar, there is trap.
but after you presented something with a uniform trap, with a box trap.
Oh, uniform box trap.
Yes.
Box trap is the boundary, it is 0.
No, there is 0.
The condition for the box trap.
And there is no effect of this box shape.
No. The box trap, on the boundary of the box, the wave function is 0. It's forced to be 0.
And if you don't take a square, but a circular trap, this trap.
Oh, yes, I tried, but it becomes messy.
Okay.
Calculation becomes a little bit messy with the hexagonal trap. You have to define it, but you should take it, and it is always possible. Triangular trap. So the wave function is forced to be 0 on the boundary.
There are some other questions.
But there are experiments being done with box trap. Many experiments are being done with the box trap.
With dipoles.
Hmm?
With dipoles.
No. Only box trap is available in the market.
Yeah.
People are doing experiment. Now, not with dipolar system or with spin orbit coupled system. Yeah. No, you can also have a triangular one. So if you have a rectangular box, then that means traps in the X and Y plane are different, the two frequencies. Then the square lattice will become a rectangular lattice. If the harmonic trap in the X and Y direction are different. Huh?
Yeah.
More stable in the triangular lattice. Is possible. No, this is stability, but if you shake it, move it, one could be more stable than the other, probably. That's what you are saying, no? Yes, possible, yeah. But the difference in energy is very, very small.
Yeah, that's right.
Yes. Okay. But
Okay, I don't see any more questions. Sorry.
So, do you generate these configurations by a sudden quench
by
theoretically? Do you quench something, temperature, or
no, there is no temperature.
what do you quench to create this?
This thing.
Yeah, how do you?
Oh,
do
that
this?
how do you do? The simplest way is this. This figure. You see, you can give this as initial state and do the calculation. It becomes sorry.
The interaction.
I don't know. Yes.
It's imaginary.
It becomes that imaginary time. You give this as the initial state. It becomes this as the final state in the calculation. But I don't have control. It can go to another state depending on the trap. But like between this and this is more number of atoms. But for same number of atoms, it can go to two different structures from the initial state. So you need a guidance, you have to select. I'm showing those states which are really symmetric. It has some spatial symmetry. But that could be ugly states also.
Okay, any more questions? If that's not the case, let's find the repeat speaker again.
Okay.
And we have the poster session now.